Last class, we looked at, we tried to keep it easy. We looked at the history of motors. We looked at why electrostatic motors are in common, what the problem is, and why electromagnetic motors are the ones that are used in industries as well as in pretty much all applications that we know of. And then finally, we ended the class with looking at a biological motor, which is basically how our muscles work. And whatever we covered in last week, none of that will be in your homeworks or exam, but whatever is going to be covered from this week on is going to be in your homeworks as well as in your exams. Right. So last class, we ended with looking at laws of motion, in particular linear motion. But this is not particularly useful for our case because in our case, when we have these motors, we're only going to consider rotational motors. There are another class of motors called linear motors, but the operating principle is extremely simple compared to rotating motors. So you take a rotating motor, think of it as a paper roll, and just unwind it. Whatever you put it flat, that's basically a linear motor, right? So operationally, it doesn't change. The only thing is there we'll talk about angle here, we'll talk about displacement there, we'll talk about torque here, we'll talk about force. So those are the only difference between a rotational motor and a linear motor. So therefore, we're not going to cover the theory of linear motor. It's pretty much anybody can self-teach it if they know how rotational motors work. So these formulas are not particularly useful in the way they are defined right now because each of these variables, if you look at these force, acceleration, velocity, all of these are three-dimensional variables. When we have a rotational motor, there is only 1 degree of freedom there. Only the angle of the motor can change, right? So we have 3 degrees of freedom in these systems, while there we just have 1 degree of freedom. So this is more overcomplicated way of expressing things. So what we would like to do is redefine these terms in terms of rotational dynamics, and that's what we're going to be doing in today's class, and we're going to look at some examples as well. So the final goal of this lecture and tomorrow's lecture is to define this one particular equation that I wrote last class for the mechanical system. And we want to see how this equation comes about. And once we have figured out what this equation is, and more than just the math of it, we want to try and get an intuitive feel for what's going on, right? Because the math you'll definitely forget in a couple of years, but once you get a feel for it, you're not going to forget it. So we want to see and get a feel for what each and every one of these terms are, look at some real world examples to kind of reinforce what we are going to be learning today. Okay. So let's start off with a very simple case. We have a rod, a metallic rod with a stiffness coefficient that's infinite, right? And again, if at any point anybody has any questions, just stop me and just call my name and you can raise a question if you can pass this around. And today would be the third class of one of 3 classes in which you should have participated to get a 1 point. Again, I don't want any of you to feel pressured. If you're not still ready to participate in class, it's okay. I will provide compensation points towards the end of the semester so that you can still get the full 25% points. But I still encourage you to participate though. Okay. So, Ben.
Are you supposed to participate once per class?
So once every 3 class, you'll get the points. But I would recommend participating every class. Multiple times a class is also good. But as far as record of points, just once every 3 class. I do post it on Canvas. There is a assignment called participation lecture 1 to 3. So just keep a track of it. If you have it 1 point there, you're good for the 3 classes. And then release it again after every 3 classes. There will be another assignment posted there. Okay, so we are going to consider a rod that is pivoted and it can only rotate. It cannot linearly stretch because the stiffness coefficient we're going to assume is infinite. So it cannot stretch in this direction or elongate in any other direction, right? And let this be at some angle theta. And it has a velocity at v. And I'm drawing this velocity purely perpendicular to the radius because there cannot be any component parallel to it. As I just mentioned, it's a very stiff metal, so it can't be stretched or pulled or compressed or anything. And this is the case we're going to always assume with all the motors. We will see cases where this will break and fail, but for our analysis, we're going to stick with it. And we want to look at what the torque of the system is going to be and what the rotational speed of the system is going to be. All right, let's start off with a simple case. So let me draw it as a simple 1-line diagram. We have some radius r, some angle theta, going with some velocity v in the perpendicular direction, and it's pivoted to the single point, so all it can do is rotate and nothing else. Right, so I'm going to give it some time delta t, and the position of this rod changes by an angle delta theta. What is going to be the displacement of this rod in this direction?
Delta theta times R.
What was it?
Delta theta times R.
Delta theta times r. So our displacement is just going to be r times delta theta. And from that, we can get our velocity pretty straightforward, delta s by delta t. So fundamentals, delta theta by delta t. And this we are going to define as a new term, r times omega, which is the rotational speed, and the units for it is going to be radians per second. We're always going to stick with SI units in this class. I think this will work. All right. So we're going to stick with SI units in this class. So that's going to be radians per second. And this is the easy way of deriving this expression. I'm going to do a little bit of a roundabout way, and there is a reason I'm not crazy. But we are going to take a look at how to do about it, this in a little bit of a different way. So I want to see what the displacement of this is along the x-axis, and what the displacement of this is along the y-axis. Right. So this distance was given as r times delta theta. Right. This angle is theta. Basic geometry would tell you that this angle is going to be theta. Right. Sorry. Theta. This angle is going to be 90 minus theta, so on and so forth. So this distance is going to be, can anybody give me what this distance is going to be? What delta x is going to be? What delta y is going to be? There are only one of two possibilities. So just throw it out and you'll get a point for today. Yep.
I don't have an answer to that, but I was wondering what delta S was.
It's the displacement, basically the distance
Oh, okay.
from this
Thank
point to
you.
this point. Anybody? Yep. Ben.
The bottom one is sine, upper one is cosine.
Thank you. Is the should there be a positive sign, negative sign?
I think they're both positive.
All right. So as this rod rotates, this length is going to increase. Right? If we assume this is 0, 1, 2, 3, 4, and 5, as the rod rotates, this is going to increase. But what is going to happen to the projection on the x-axis? Decrease, because as this rod rotates, right? When it's flat, it's going to have the longest distance. When it goes to 90 degree, the x component is going to get 0. So the x component is gradually reducing. So as the angle increases from 0 to 90 degree, this one goes to 0 when the angle becomes 90 degree, but before that it's a higher value, and when it's on this axis, we have the maximum distance. So delta x is basically going in the other direction. Right? So now that we have our displacements defined, let's look at the velocity component. So Vx is just going to be delta x divided by delta t. And then we have r delta theta times sine of theta divided by delta t. This itself, we can replace it. So sine of theta is just the y value divided by the radius. That's the definition, right? So this itself is just y divided by r. So that ends up being minus y delta theta by delta t, or minus y times omega. And this is the x component of the velocity. So it's somewhat counterintuitive of the cross coupling that happens. And then the same thing can be done for the x component or the y component of speed. Comes from basically this r delta theta cos theta, r delta theta cos theta divided by delta t. And cos theta itself is going to be the original length x divided by the radius r again. Definition of cos theta x divided by r. So we end up with same r cancels. X remains delta theta by delta t. We already defined that d theta by dt as omega. So the x component of velocity depends on the current value of the y, and the y component of velocity depends on the current value of x. Anybody want to tell me why that cross coupling is happening? There's nothing magical about it. It's purely just the trigonometric nature of our arrangement, right? So the projection of this is going to be sine of theta, but as this rod rotates, what is the rate at which that's going to vary? Differential of it. Sorry, the projection of this is going to be cos of theta, and the rate at which it changes, the projection changes, is going to be the differential of it, which is going to end up being negative sine of theta. And negative sine of theta itself is the y component. All right, so that's all the cross coupling term is explaining. So if you look at the displacement itself is purely just along the x direction, but the rate at which this displacement changes is going to be a function of the y component. So that's all is happening here, nothing fascinating. So our velocity itself, our net velocity, so this is the x component, this is the y component. How do I get the net velocity component?
Square root of bx by.
Perfect, thank you. V square, Vy square, hopefully we end up with the same expression as before. X square plus y square times omega square, just omega. What is this term? The square root of x square plus y square?
R.
R. Which is in this bit? R omega. So it's the same expression we got as before. It should be the same. So there's a reason I went through this roundabout way, and we'll see that in a second. But before I go that route, can anybody tell me what the expression for torque is? So let's say that this rod is experiencing some force F along the direction of velocity. There could be another force that's parallel to this rod, but that is useless again because this rod cannot be stretched or compressed. So even if there is a force, we are going to ignore it because it's not going to cause any energy transfer in this because it's not going to be able to displace the rod given that it's pivoted. So even if there is some force in some odd angle, it can be resolved into this perpendicular component and this parallel component. Only the perpendicular component is of interest to us given the nature of the arrangement that we have. Right. So given that this has a force F in this direction, what is going to be the torque? Yeah,
R.
force times radius. Why is it? Radius times force. Definition.
Yeah.
Alright, so why don't we define it as r square f or rf square or r by 2f? There are infinite number of combinations that we could have chosen. Why that particular representation? Right, so let's look at our expression for energy. This we have defined as integral f dot dx. And this itself can be broken down into two components, fx component along the x direction and component along the y direction. And this again can be broken down into two components, delta x and delta y. Right? So if we look at our diagram here, fx would be, sorry, fy would be this component, and this would be the negative fx component, right? Because we are measuring x along this direction. So whatever projection we put here, that would be the negative of whatever fx value we get. So this is our y component, this is our x component. Given that, we can substitute those values over the, so this is a dot product, right? What that basically says is if I have this, let's say I have this duster and I put some force on it and it starts moving, I'm going to put a force both in the perpendicular direction as well as in the horizontal direction. But only the component of force that moves the duster does any work, right? The perpendicular component is not doing any work, only the horizontal component is doing work. That's what the dot product is representing. It only considers the component of force along the direction of motion. If delta y is 0, then the component of force Fy along the delta y direction is useless. It's not going to do any work, right? So that's what the dot product is indicating there. So given that this is Fx, Fy, delta x, delta y, what will this be? Integral? Just dot product. Anybody? When you have two vectors, xy component, what's the dot product of it? Okay.
Fx times delta x plus Fy times delta y.
Okay, there are no wrong answers in this class, so give it a shot. Okay, we are all here to learn, so don't be hesitant. Okay, so let's substitute for these values. We already have an expression for delta x and delta y somewhere on the left of the screen there. So let's substitute those values. I'm going to write this around like this. It will become clear in just a second why I'm doing that. X delta x. I haven't done anything. I just swapped the terms. Okay, so this, again, I'm just going to swap the order of multiplication. Again, nothing changed. So once I substitute for delta y, which was x times r times y times delta theta. Sorry, delta y was x times delta theta Fy minus, and delta x was delta x by delta theta was negative y delta theta by delta t cancelled, so it's negative y delta theta, negative y delta theta fx. I can take out the delta theta term outside, so it is x Fy minus y Fx times delta theta. I'm just going to replace it as d theta variable of integration. What is this term? So this was dot product. What is this term? That is the definition of cross product. Okay. So when you have a two-dimensional vector, so in the bracket, we have a vector with coordinates x comma y, and we take a cross product with a vector fx comma xy dx. That's the definition of cross product. So when you have ijk xyz, say fx, in case of 3D, right? In our case, it's just 2D. So the cross product of the ith term is just this times this minus this times this, yfz minus zfy. And this term is this times this minus this times this. This term is this times this minus this times this, right? So for the kth term, it's going to be xfy, this times this times this minus y times fx, which is what we have there. So it's basically a cross product. So this itself is our force vector. And what is this vector? X comma y. Okay.
Position,
What was it?
position.
Position. It's the radius, right? The position at the tip of the rotating rod. So that's effectively the radius vector. So what we have is radius vector cross product, the force vector times d theta. In this, we want a nice way of representing this particular term, and that we are going to define it as torque. So that's the reason torque is defined as radius times force. It's just a shorthand convention of representing it in a very simple form. There is no reason for any particular underlying physics or anything for the definition. Right? So in our case, we said that the force is always going to be perpendicular to this particular rod. When we look at a machine, that needn't always be the case, as we'll see. When the rotor is rotating and there are windings and stuff, the windings would experience force that is pulling the windings out, at the same time rotating those windings as well. That's why in the motor there are things called retaining sleeves, because when the rotor rotates, you don't want the windings to come out due to centrifugal forces, as well as to retain the conductors from moving when there is a force that's pulling them in the direction outwards or compressing them inwards. But that is not a component of what we are interested in analyzing. In this course, we are only interested in the component that would actually rotate the motor, which is going to be always perpendicular. So in this class, we are always going to consider only the component of force that is perpendicular to our radius. So this in turn, it's the magnitude of the radius times the magnitude of the force times sine of theta. Go from here to that expression that I've written on the right, it's just basic algebra. You can substitute those values and you'll see that all the expressions that I'm writing here are exactly one and the same. And this is same as saying it's radius times the force that is purely in the perpendicular direction, right? So going forward, if I give the force purely in the perpendicular direction, you don't have to worry about clockwise, it's just radius times the force. Anybody got any questions so far? The units for this is going to be Newton meter. Okay. So in this case, when I gave the units for our omega as radians per second, we typically want to express this in terms of rotations per minute. Anybody want to tell me the conversion factor? Radians per second to rotations per minute. Anyone who has an answer? Take a guess.
60 over 2 pi.
Wasn't?
60 over 2 pi.
Okay, thank you. So you want to go from seconds to minutes, so multiply by 60. You want to go to radians to rotation. So in one single rotation, you have 2 pi radians. Right? So divided by 2 pi. This is roughly equal to 10. So if you want to do a quick calculation, just multiply omega by 10. But the correct value should be 60 by 2 pi. Right? Okay. Anybody have any questions so far? Great. So while we are on the topic of torque, let's complete the last expression. So this is our definition for power. Right? So, sorry, energy. Power itself was dW by dt. So we have d by dt integral of d theta. Order of differential of this integration doesn't matter in this case. So tau times omega, torque times omega, right? So that's going to be a power, and of course the units is watts. In the homework, make sure you enter the units, because just by looking at the units, you can clearly see if you have done something wrong in your homework.
Could you possibly write that bottom line again on the top? It's a little hard to see with the.
Oh yes, will do. Power, the rate of change of energy. So we have d by dt of d theta. You can check the order doesn't matter. So so we're going to look at first equation that I had, first part of this equation. So the equation that we are trying to get to is tau em is tau L plus j d omega by dt plus d omega. So we are going to look at how this comes about. Okay, so we are going to take a simple case where we have a cylindrical shaft, not too uncommon in case of the motors. And we're going to find out what the inertia of this shaft is going to be. All right, that's the term there. So the J term is the inertia. And we want to see how this relation comes about. So this is not a definition. We have defined everything that we need to. We have defined the torque, we have defined the power, we have defined the omega, we have defined the angular velocity. And that's about it. So for every term that we had in our linear motion, right, we have defined an equivalent system in our rotational dynamics. We can define, if you want, angular acceleration, that's just going to be differential of the angular speed, and so on and so forth. What is the differentiation of acceleration? Anybody know? Differentiate distance, velocity.
Jerk.
Jerk, differentiation of jerk.
I don't know.
Right, so it goes jerk, snap, crackle, and pop. Each of it a higher order differential of the previous term. So in our rotational dynamics, we are not too much interested. It would pretty much stop with dw by dt for most analysis, which would end up being angular acceleration. If you want a symbol for it, typically we use alpha, radians per second squared. Okay, so we are going to derive this particular expression where the torque of this inertial system is going to be J times d omega by dt. If this is not a definition, we are going to derive this. So let's start off with a tiny segment d theta. So just an incremental volume that doesn't look like an incremental volume, but think of it as a tiny volume that I've drawn there. So this whole length is L. So this tiny incremental length is dl. If this is radius r, this tiny incremental separation is going to be dr, right? And this distance itself is of course going to be r times d theta. And then the density of this shaft, we are going to call it rho, which is the density, kg per meter cube. What is going to be the mass of this incremental volume? You have all the information there to figure out the mass of this incremental volume. The volume of that incremental element that I have drawn there. Very simple question. So it's just yep, say it.
R d theta times dr times dl.
So just a small incremental volume of some cylindrical coordinates. So the expression is just going to be this length times the vertical length. So this is our incremental. So this is the incremental volume, and to get the mass, just multiply the incremental volume by our density rho. What's going to be the force experienced by that incremental volume as this mass rotates? What's the relationship that links mass and force?
Mass times acceleration.
Mass times acceleration. So the force experienced by this incremental volume that I've considered, the incremental force is going to be the incremental mass times the acceleration dv by dt. Right? For v, again, we want to go into rotational coordinates. So what is v in terms of a rotational system? We just derived v in terms of angular speed.
Or omega.
R omega. So v is just r omega. R itself is not changing. That was the first thing we said. Material is stiff. So it's just r times d omega by dt, which ends up being the angular acceleration. And let's substitute for dm. So we have r there, we have another r here, we end up with r squared. I'm going to swap these order around. R squared, dr, d theta, dl, rho, d omega by dt. What is going to be the incremental torque experienced by this element? We have the incremental force. What is going to be the torque? Is multiplied by r. So just r times r df, which is going to be, put another r there, r cube, dr, d theta, dl, d omega by dt. How do I get the total torque? That's the incremental torque. What do I do to get the total torque experienced by this block of steel that's rotating about a central axis?
Integrate across the entire radius and length
And
and the other dimension.
so there are three things here. So let me do the last one outside. So that's going to go from 0 to the full length. Again, people generally do not like to have the same limits of integration as the variable that's being involved in integration, but as long as you know those are two different things, that's absolutely okay. So the other one that's integrated is the angle. So we are looking at a tiny incremental angle. We need to look at the full angle, so it'll go from 0 to 2 pi. And then the last one is going to be our radius, going from the center of this mass, where radius is 0, to all the way outside. So if you're uncomfortable putting small r, put a capital R, but I'm just going to go with small r. dr, d theta, dl. Each of these integrals are independent of one another. The speed at which it's rotating is independent of any of these internal terms. And the limits itself, each of these limits do not affect the other one. So you can integrate each of these as separate entities. So you end up with, if you integrate r cube dr, you end up with r power 4 divided by 4. And then 0 to 2 pi. If you integrate that, you would end up with 2 pi. And then dl, if you integrate from 0 to L, that's just L with the limit 0 to L. So you end up with L. And then finally, dw by dt. This, we are going to call it moment of inertia, right? Because all of these variables involved here are constant. So our torque for a spinning steel or any material that is not getting deformed, the torque is going to be equal to J times dw by dt. If you assume it to be a pure cylinder, this is the expression for inertia. If you assume some other shape, the inertia of course changes. Right? Anybody got any questions so far? Yeah.
Is there a reason you put the mass all the way on the outside? Or is that like across the whole
Which expression? This
DM
one?
inside the cylinder? I'm talking about the actual diagram, like your picture.
Uh-huh.
Is there a reason you put DM like only on the outside, like on the,
This DM,
yes,
is there a reason why I put this where? Really?
like in your picture, your arrow.
I don't have a DM arrow here at all. So this is DR.
Oh, I didn't see that. Okay.
Yeah, this is, sorry, my handwriting is terrible. So that is D small r. Because it's the incremental length along the direction of the radius.
Okay.
Was that your question?
Yeah.
Any other questions? Yeah.
So that like section of the cylinder is rotating inside it, or?
No, it's the whole cylinder that's rotating. So if you think of this marker, right? It's pivoted along the vertical point and this whole thing is rotating. So think of it like the rotor. The whole rotor is rotating pivoted along the center. So we basically calculated what the inertia of a rotor would look like. Any other questions? So there's another way of expressing this. What is going to be the volume of the cylinder? You have all the dimensions needed to calculate the volume. It's a very trivial question. What is the volume of the cylinder? Oh, please don't let me down. That's a very trivial question. Yeah,
Pi r squared times length.
thank you. So the volume of the cylinder is just pi r square times L. So let's take out the pi r square L terms outside. So this 2, 4 cancels out. We just have our denominator 2. So if you take those terms out, pi r square L times rho, all we are left with is r square divided by 2 times dw by dt. What is this term?
Mass.
Mass. So that's actually going to be the mass of the cylinder. So textbooks, you might typically see this expression given for the inertia of a cylinder. So just another way of representing it. And This is somewhat important, like you would have seen this in, if you look at these ice skating, figure skating and stuff, right? Whenever you do figure skating, you want to keep this, the inertia term is what you change around. You can't change the mass term, but you can change the radius term, right? When you put your arms out, this radius term increases quadratically. So you can basically make this inertia extremely large. And because of that, the speed will come down. We'll take a look at why the speed will come down in a second. But when you put your arms close to your body, the radius becomes very small, the inertia becomes very small, and you will start to spin pretty fast. So that's all the figure skater is doing. So once we have this, let's look at what the energy in that inertial system is. It is integral d theta, which is same as substituting for this value, j dw by dt times d theta. D theta by dt is just the omega. So it's integral j omega d omega, which is half j omega squared. Anybody got any questions? So let's look at a quick example. So let's say lifting a weight of 10 kg, not too much. I'm tired from leaning on the wall last week. So let's say it's about 10 kgs that I'm lifting away. I wanted to draw me, but it looks like a creature from Stranger Things. Bear with it. And the average arm span is about 2.5 feet. I think that comes to about 0.75 meters. Right, so let's say the state when the weight was down here, I was holding it, that's going to be the zero energy state. And then when I lift it, we want to figure out how much energy is being transferred, what the torque is, and so on and so forth. So in this raised position at this 90-degree angle, what is the force that my arm is experiencing? What is the only force acting in the system? Gravity. So you're basically working against gravity. Right? So mass times acceleration, which is 10 times, I'm going to assume it's 10 meters per second square. So we have 100 newtons. Okay. What is going to be the torque? And the direction of this force is always going to be perpendicular downwards, right? So there is going to be no other component for this force. So what is going to be my torque? It's radius cross product force. And if my force is perpendicular to the radius, then I can just leave it as radius times force without not worrying about the cross product term. So that's 0.75 meters, which is the length. I'm assuming we are measuring the torque experienced by the muscle in the shoulders. The force is 100 Newton. We end up with 75 Newton meters. So let's say it took me about a second to go from initially zero angle to 90 degree to lift that weight. So delta theta is pi by 2. Okay. Started off at 0 degrees, went to 90 degrees. Those of you in the back row, can you see up to this line if I write here? Right. So what is the angular speed? Anybody?
5/2.
5/2. So just delta theta by delta t. So since the time it took is just 1 second, that's just 5/2. Always give the radians in units. Okay, so what is going to be the power? Tell me the power. We just derive that expression.
75 pi over 2.
Okay.
75 pi over 2.
75 pi over 2. So that's torque times omega. 75 times pi over 2. And that comes out to, somebody wants to do the math quickly. I think it comes out to about 118 watts. Oh, yeah, sorry. So what is going to be the energy? If I know the power, what is the relation between the energy and power?
The energy over D,
So what is power in terms of energy?
rate of change. Energy.
Rate of change. No, sorry, what is energy in terms of power? My bad.
You integrated.
Integrated. Can you give me what the answer would be?
Like the expression?
The final answer for what W would be. You have all the information to be able to calculate it.
118 joules, right?
118 into
118 joules.
118 joules. Is that correct though? So power is P dt because, sorry, power was dW by dt. So energy is integral P dt. So let's say that's P times delta T. Question is whether the answer is correct. So 1 second, 118 joules. Is that answer correct? No, why not?
Because you're not doing any power. The rate, the power you're doing changes based on the angle.
Perfect. So the torque, we have to be quite careful when we do this particular expression here. The torque is not always a constant. So at this particular angle, that's where the torque is the highest. But when the weight is at the bottom of the, when it's at 0 degree, the torque is absolutely zero. There is a force pulling on my arm, but there is no rotational torque. And assuming my arm is stiff enough that it doesn't bend with the weight, there is no displacement happening. So when the weight is in this position, even though my body is expending energy, it is not getting transferred to the weight that I'm holding, right? So we have to be careful when we do this. So we had another definition for wherever I had written it down. Torque integral tau dt. So when angle theta equal to 0, what is the torque going to be equal to? 0 Newton meter. So that's what we just saw. And the weight is at this angle, there is no rotational torque. But when the theta is at 90 degree, we calculated the torque to be this value, 75 Newton meter. What is it going to be for any particular angle theta? As a function of any angle theta, what is the torque going to be? Anybody? What function has a property that it has a peak at 90, 0 at 0? And that's purely a projection of the force, right? So let's say my hand is in this 45 degree angle, then the force is still in this direction, right? A portion of the force is trying to stretch my hand out. The other portion of the force is what is creating the rotational torque. And this angle is going to be same as this angle theta, right? Oh, sorry. 90 minus theta. So the projection of that is going to be cos of 90 minus theta. Sine of theta. You don't even have to look at the geometry. It's just, if at 0 you want 0, at peak you want 90, you want peak. There's only one function that can give you the particular curve. And we know this is all trigonometric in nature, so you can make a very good educated guess that that's what it's going to be. So once we have this, let's plug in the expression. So we have 75 sine theta. Our energy going from this resting position to this 90 degree. I need to integrate from 0 to pi by 2. There is a variable of integration there. That is my torque changing as a function of theta times d theta. And anybody remember what this integral comes out to? It's a very nice integral value to remember too, because we'll come back to this again and again when we go to Fourier series and we look at power electronics. Anybody know what this value is? which is 1. So 75 joules. Significantly different from our initial calculation, which is definitely not correct. So this is in some sense correct. If we call it instead the peak torque, peak power. So if we had to call this the peak power, then that's absolutely correct. But that is not the average power. So now to get the average power, take the energy that's being put into the weight going from 0 to 90 degree divided by the time it took to go to that weight, dW by dt, it took 1 second. So 75 watts. So our torque itself, peak torque was 75 Newton meter. So to put that in perspective, anybody know what the Tesla Model 3 motor torque is, real motor torque? Anybody from Go for Sports or? So it's about 190 Newton meter. And I took a very small weight, right, 10 kgs. I'm sure most of you in this room can easily do 20, 30, 40 kgs. So the torque that you can, peak torque that you can produce is much higher than what the Tesla motor can do. What's the difference though?
It's running at thousands of RPMs.
Okay, so this is at around, I think, 5,400 RPM. And the power, 400 kilowatts. Okay. So it's an enormous amount of power. We are doing it at 75 watts. So it's orders of magnitude higher, the peak power that the motor can generate. So that's the difference. We can generate quite a bit of torque. That's somewhat very fascinating about how our body works. Given the structure that we have, it's able to generate this much amount of torque, but we can only do it quite slowly, and we cannot do it continuously. Okay? This can do it repeated again and again and again and again for 10, 20 years without breaking down. It's going to be not possible for us to do that continuously, right? Do you have any questions? If
Yeah. I'm getting the average power. I don't see how that's 75 watts. Like, where does that come from?
Oh, it comes from the total energy
Okay.
divided by the time it took to go from 0 to pi by 2. So dW by dt, right? So the time it took was delta t was 1 second. Okay. And the energy transfer was 75 watts. So the energy transfer divided by the time taken is your power. Within this, so this is the average. So if you look at what the actual power plot looks like, at time t equal to 0, the power would have been 0. At time t equal to 1 second, the power would have been 118 watts. That's the one we calculated, T peak. At angle 0, P minimum, power is 0. The area under this curve is going to be the energy, right? Divided by the time period is going to give you the average value, so the mean value. Sorry for that, right? Do you have any questions? Okay. So let's look at another example of flywheel energy storage. Anybody have from mechanical engineering? Right. We have this professor Eric Severson, a brilliant guy in mechanical engineering, who works on this flywheel energy storage. He was part of his PhD thesis, and he still continues to work on it. When we have, so when we looked at the energy in total rotor, inertia, and so on, there was some sufficient amount of energy, half j omega squared. So in traditional power system, you have the synchronous generator, not permanent magnet though, the rotor would be excited separately, but the functional principle is pretty much the same. And when there is sudden fluctuation in so the generator keeps spinning at some speed, and then let's say suddenly an industry turns on their whole load, or a residential complex turns on their whole load, where is the additional energy going to come from? Right? If you have hydroelectric power plant, it takes some time for the valves to open and the system to kick in and catch up with the power. Or even if you have coal power plants, can take hours or 6 to 12 hours to sync up to the power that you extra demand you need. If you have a nuclear power plant, that could take months or years to catch up with the power demand. So in the transient temporary period, when a hydroelectric power plant, which is somewhat much faster to respond to these transient power demands, the energy stored in the inertia of the hydroelectric the motor that's rotating, generator rotating in the hydroelectric power plant is what is going to provide the additional energy that's being required on the load side. All right, if the inertial energy is not there, then the whole grid would collapse because there is an additional energy needed, but there is nothing on the generation side that's providing the energy. So the system would start to collapse. So this is extremely critical in traditional power systems. We have this inertial energy coming from these rotational generators that we have. But as we transition more and more to photovoltaic system, there is no rotational element storing that energy. Right? So this is one of the biggest problem with going to 100% PV. Is something that we need to address is to provide that additional inertia, because when there is a sudden load that demand comes up, something needs to satisfy that load demand. Otherwise, the voltage, the frequency would start to collapse in the system. And once it collapses, it could take days to bring it back up online. So you definitely don't want to have that happen. Right? So as we transition more and more to this PV-based system, we need to figure out other ways to store this energy. And one way the grid stores the energy is through flywheel energy storage. So all it's basically is so we have in the previous case we found out the inertia of our system, right? If I remove the formula correct. Times L, I think. Yeah, that should be correct. So this was the inertia. If you can take a disk that's extremely large in radius and spin it to very large speed, and then the energy itself was half j omega square. So if we can make this large and then spin it to extremely large speed, we can store huge amounts of energy in this flywheel. And when we need that energy, suddenly when the load demand increases and we need that energy, we can make the motor operate as a generator. We saw in the last class during the demos that generators and motors are one and the same. So we take energy from the grid, push it into this flywheel, store it and keep it there spinning. And then whenever the load suddenly demands it, we will take out the energy stored in this inertia and send it back into the load. So this is a very interesting way of storing energy, but this is not quite popular though. So our grid, less than 0.5% of the energy storage mechanism of our grid currently is flywheel energy storage, and just a meager 45 megawatt hour. Anybody know what the energy consumption of US was for last year? So it was about 4 billion megawatt hour. So way higher than the energy being stored in a flywheel. The most common way that energy is stored in the grid is called basically using two reservoirs. And you have one reservoir at elevated height, one reservoir at a low height, and you use a pump to push the water from this to the higher reservoir and store the water there. And when you suddenly need the energy, this pump now would become a generator and the water flows from the top to the bottom reservoir and you can take the energy out, right? So this is called pumped energy storage, pump storage. So this is the most common way of storing energy in the grid right now. Is there a reason why flywheel energy storage is not that popular? Anybody want to tell me what the limitations would be? It seems almost too good to be true. Because if in this case, when I store energy like this, I don't scale that much, right? It's just the mgh, the potential energy. So again, by the way, here, if you put the formula mgh, you should get the same result. So we had 10 kg times gravity was 10 meter per second square, and the height that changed was 0.75 meter. So you should have gotten 75 joules, right? So all that energy that we can store is mgh. So if you double the weight in this reservoir, double the volume, you can only double the energy storage. But in this case, if you double the speed, you get 4 times the energy storage. If you make it 10 times faster, you can get 100 times the energy storage in this flywheel mechanism. So what is the problem? Yep.
There's just mechanical limitations to being able to make something like that.
Perfect. So there are mechanical limitations. There are two problems. First, we have bearings which could fail. We don't have systems that can do very high speeds. And that's the area where the professor in mechanical engineering is working on, basically using a magnetically levitated system. So the rotor right now, when we had these motors on the table, they're not floating in air. There is an air gap separating the rotor and the stator, but there is a bearing that's attached to the rotor, which is resting on the stator. So the bearing can only rotate at so much speed before it starts to break down. So that's the biggest limitation with how fast it can rotate. So if you can magnetically levitate this rotor, then there is no limitation on the bearing. There is a second limitation where so right now we have considered the metal to be stiff, but if you rotate fast enough, anything will become, it will start to become floppy and start to break down, right? Because there's going to be a lot of centrifugal forces pulling on the rotating system, and it's going to tear it into pieces. There is this channel Slow-Mo guy on YouTube. Have any of you watched it? Right, I'll post a link to the video where they basically spin a disc, and when it spins fast enough, it will act as if it's like a plastic wrap or something. It will just start to vibrate and then at some point completely fracture out. So let's look at the amount of energy that one of these flywheel systems stores. So there are only a total of 6 units in the US that have this flywheel energy storage, very tiny fraction. One of them is in Texas. And the energy rating of that is 2 megawatt hour, right? So there's going to be our energy. And the inertia that so 2 megawatt hour, it's 10 per 6, R2 minutes. And then minutes to seconds. So once you do the multiplication, that comes out to 9 into 10 to the power 9 joules, right? And the speed at which the system is rotating. So that is not given in their website, but we are going to make an educated guess based on the other motors, flywheel systems that we know of in the speed at which they rotate. So typically around 18,000 RPM. Going more higher than this is a little bit tricky. We have to do a lot of engineering to make the materials stable, but especially as it goes to higher and higher power, it becomes even more difficult. So let's convert this to radians per second. It should be roughly a tenth of it, because last time I said going from radians per second to rotations per minute is 10 times. So 18,000 times 2.5 divided by 60. So this is just a factor of 10. That should roughly be 1,800. The correct value is 1885 radians per second. So from that, it's pretty straightforward. We can calculate what the inertia is. So substitute in the formula, 2 times E divided by omega square. So 2, 9, 10 to the power 9 divided by 1.885 into 10 to the power 3, the whole square. So this becomes 10 power 6, 10 power 3. Let's call this roughly 2. I'm fine with doing any kind of approximation if it makes our life easy. So 2 square is going to be 4. So that comes to about 4.5 into 10 to the power 3. What is the units of inertia?
Kilogram meters to the fourth?
What was it?
Is it kilogram meters to the fourth?
Kilogram, meter. Well, I had written another expression for inertia in terms of mass and radius. You did ask me the question to what would happen if the radius doubled. What happened to the inertia if the radius doubled? It was r square, right? It became 4 times. So you have mass times radius square. So you would end up with kg meter square. Okay. So the correct value, this is a whole bunch of approximation. The correct value that I calculated before coming to class was 5066. Not too far away from what we approximated. Kg meter square, I should write at the bottom. So the inertia comes to the exact value 5066. kg meter square. So the radius of this system again is not given, but we can once again take an educated guess based on other systems that we have of this power scale. It's about 2 meters. And the way this system would typically be is it's not our typical motors that we saw in the lab today on Friday. So those of you have seen the quadcopter motor, right? The rotor is on the outside. So these two, the rotors would be on the outside and it would be a heavy block of steel. And this whole block of steel is going to be spinning at 18,000 RPM. And that's where the energy is all stored. And the way they store these is they build these huge concrete foundation, drill right through those concrete foundation, hide those motors, rotate spinning motors inside it, and then cover it with layers and layers of concrete. Because if one of those were to shatter, it could bring down the whole building along with it, right? So it's extremely high speed, so much extreme amount of energy that's being stored within it, right? 9 into 10 to the power 9 joules. Think about the energy that we pushed into the block that we lifted by our hand was 75 joules. So you can think of how much weight you need to lift to get to that particular amount of energy, right? So it's extremely dangerous. So this is, let's assume this to be the radius. Then we can find out what the mass of the system is going to be because we had half m times r square was our inertia. So we know our inertia, we know our mass. Yeah, sorry, we know our radius. Substitute all those, the mass comes out to 2533 kg. Or basically half of that, right? 4 divided by 2. So 2533 kg, roughly the weight of an SUV. Right, so that's the mass that they are spinning. So take a SUV, put it 2 meters away and spin it out 18,000 RPM. That's what they are trying to do by storing that energy there. And that's the reason it's not too popular because of all the danger associated with it. And also the cost that goes into this because reservoirs, you can easily find them. One at the lower level and one at the top of the hill. All you need to do is put a pump and you've got energy storage right there. But this is something that needs to be constructed with a lot of engineering and stuff. Right, but if there is a material breakthrough and this can go to much higher speeds, this would far outpace the energy storage that you can get with a reservoir because just by doubling speed, you get 4 times the energy storage. Right? Anybody have any questions? Okay. We have a little bit more time, so let's look at one more example. Anybody thinks I'm going too fast? Anybody still awake? Make sure I'm recording the Zoom video. Too late to do that now. Oh, by the way, I do have this video recorded on Zoom, but do not attend the Zoom class. You are expected to be here in person. The Zoom recording is only for people who have a full-time job and they can't participate, or you're sick someday, or you have to take an interview and you can't be. The Zoom will be recorded and you can watch it live. Otherwise, after class, within a couple of days, I'll post it on the media gallery on Canvas, and you can go watch it there when you're trying to do homework or preparing for your exam. All right, but you're all expected to try to attend the classes in person so that we can have a conversation here. Okay, so the next case we are going to look at is the case of a fan. So right now we have solved one part of our equation, which was so when we had our expression tau em is tau L plus J d omega by dt plus d omega. So this, we have derived it, we have analyzed it, we have looked at the energy, we looked at 2 different cases, and we have solved everything that we need to know about this has been figured out. So the second thing we're going to figure out now is this b omega part by looking at a quick example. Okay. So how many of you have been to IKEA here in Bloomington? Most of you, all of you. When you pick up your final furniture, have you seen that huge fan at the bottom floor of IKEA? Everybody has seen it? Some of you? Right, so I looked up the motor before coming to class. It's a interesting one. Let me see if I can get the document camera on. Yeah, this one right here. So this huge. So this fan right here, do you see it? Okay. So that fan rotates. I was able to find the seller for the fan and they have the specs. Stop screen share. So before class, I looked up this fan where it's sold. It's sold in Home Depot by a company called, I'm not gonna spell it out loud. Right? And last time I was in IKEA a couple of years ago, I counted how many rotations does this fan make in a minute, and there was 30 rotations per minute. And we like to keep things in SI units, so that is going to be 30 times 2 pi divided by 60, which is equal to 3.14 radians per second. Okay. So the expression for the torque that the motor is generating to rotate this fan is given by B times omega. This is a purely empirical relation, right? And you would have done this in your high school when you learned about laws of motion, right? Where you would have given this formula if you had a block that's sliding on a sloped surface and there is a force on this block, you would write down the equation of motion as the force equal to the coefficient of friction times the velocity with which this block is moving, right? Again, this is an empirical relationship. The theory involving the reasons for friction is extremely complicated. It involves electrostatic effect, it involves viscous friction, so on and so forth. Numerous different things contribute to friction. So there is no faithful theoretical model that works across all spectrum. So we just use an approximate empirical relationship here. But this too does not work in all scenarios. Say we have this case of the fan blade that's spinning in air. Different scenarios, we would use this formula, mu times V, or sometimes we'll use mu times V square, or in the case of a ball spinning in air, sometimes we can use this, sometimes this will be more applicable, right? Anybody want to tell me when you would use which one? Okay. Even in the case of the fan, when it's spinning, sometimes you want to use B omega as the expression. At other times, you would prefer to use B omega square because that more faithfully represents what is happening in reality.
If it's turbulent?
Turbulence, perfect. So when you have turbulent flow, you would, so let's go back to our rotational system. So when the flow is laminar, B omega more or less faithfully represents the what's happening in reality. But when the flow gets turbulent or air or water, B omega square is more faithful in its representation of what's happening in reality. These coefficients B in both the cases will not be the same. They will be quite different, right? And B itself is damping coefficient. Or sometimes referred to as coefficient of viscous friction. So this is applicable more when the drag force satisfies the Stokes law. In other cases, this would be more applicable. So do we do we intentionally use turbulent flow ever in any application? Or do we always want things to be laminar? So I assume everybody knows the difference between laminar and turbulent flow. So if you don't, if you go to your home and open the tap and you open it very slowly so that there is just a little of water flow in, right? You'll be able to see right through the water stream because that's a laminar flow. Or you can put a spoon in the water and you'll see a clear fountain kind of come up, and through you can see through that water and it'll be completely see through. And that is typically the laminar flow. But as you keep increasing the speed at which the water is coming out of your faucet, the water starts to become turbulent. So what basically happens is you get these vortices that form, it traps these air molecules which prevent the water from being see-through anymore. Right? So we intentionally create turbulent flow. So those of you who have worked on quadcopters or something know this from first-hand experience. So if you look at the case of an airplane, when we have this blade at some angle of attack, and when the air molecules go past this blade, we want these molecules to stick very close to the surface of the blade. And that's very critical to create lift. But in laminar flow, there is this phenomena that happens called fluid separation, where after the air molecules passing through a portion of the blade, it starts to separate out from the blade and move away from the blade. And this causes a precipitous drop in the lift that can be created in the system, and the system becomes extremely inefficient. So what they typically do is these blades are structured so that the air molecules that make contact, as they exit, they create these vortices becoming turbulent. Right? And this helps the air molecules stick very close to the blade, thereby improving the lift that can be generated in this blade. Right? So turbulent flow is intentionally created to help with lift that we have. So in our case, we are going to always assume that it's laminar, or the speed at which we are rotating is not too fast to the extent where we have to worry about turbulent flow. Or even if the turbulent flow occurs, we can always assume that this nonlinear equation that we have here can be linearized around the operating point. So if, say, the rotor is rotating at 1800 RPM and the flow becomes turbulent, we can always assume that the motor is rotating at steady state around 1800 RPM. And for perturbations in and around it, we can linearize the system using Taylor series expansion and go back to this again linear model around that operating point and design a controller and so on and so forth. So for this course, we are just going to stick with this simplified empirical model. And we are going to figure out what the torque is required for this blade that we have here. So for the fan, the IPF fan that we have there, the damping coefficient V is 51 kg. Anybody know what the units for this is going to be? So we had this equation, right? Tau m equal to tau L plus j d omega by dt plus b omega. This j times d omega by dt, units of this must be the same as units of b times omega. Right? On this side we had kg meter square times radians per second times 1 by second for the dp on the denominator. So here we have the radians per second term. So what we are left with is kg meter square divided by per second. Right? So the units are going to be kg meter square per second. And we already figured out what the rotational speed for the system was. It was 3.14 radians per second. So the torque required to be generated by the motor that's attached to this fan to rotate at that particular speed is simply given by b times omega, which is 51 times 3.14. That was around 160 Newton meter. The value is approximately 160 Newton meter. right? So in this case, we haven't considered the inertia of the fan in the attached rotor structure. Particularly for the fan of that big size, inertia would play a very big component that cannot be ignored. So our actual equation should have been tau m equal to j d omega by dt plus b omega. Just for this, to make it extremely simple, we are only looking at b omega alone because we looked at j d omega by dt as a separate case when we looked at the energy stored in a flywheel and so on and so forth. Right? So the data sheet for this motor that was available on the website does not actually give this damping coefficient at all. So how do you think I figured out what the damping coefficient is to use for this particular example? So those of you who worked with motors, ordered motors, what value does a typical motor data sheet provide? We did see the case of the rating for the Tesla motor, right? So they provide the torque. So the torque value was provided in the data sheet as 160 Newton meter. And I basically just reverse calculated what the damping coefficient was and I kind of cheated. So I gave you this and asked you to calculate the other way around. So I didn't know what this value was. I didn't derive it or anything. It's impossible to derive. It's observed empirically. So what if you actually want to figure out what this value is, in reality, they would spin it at some speed, measure what the torque is, and then use this formula to get the B, right? Just as we have, just as I have done before the class. Okay. Oh, so before I forget, there is one topic that I forgot to get into. While we are talking about energy stored in a flywheel. So this is not something we are going to derive, but you can find this in most textbooks, physics textbook, which is the angular momentum is equal to inertia times the rotational speed. Right, this is similar to what we get in our linear momentum where P was equal to mass times the velocity. Here it is instead inertia times omega. This is not a definition. We can't define it because we already have defined the momentum in terms of linear dynamics. So when we go to rotational dynamics, we need to extend it same way how we had defined force in linear dynamics, and then in rotational dynamics we derive from that an expression for torque. So we need to do something similar for this. I'm not going to do it right now because this is a term that we are never going to use in our machines course, but just for completeness, I'm going to mention a couple of observations, interesting ones. So we have derived the expression for inertia as half m times radius square, and we have also derived the expression for the energy as half j omega square. So you all would have seen this figure skating, particularly like Olympic events or something, where these figure skaters are basically skating on ice. They initially start off in a position rotating with their hands out. So what that means is when their hands are out, their inertia value is extremely large because it scales as r squared quadratically, right? And then what they do is after some time they are spinning at some speed because they've used their energy with they're using their other legs. They've increased their angular momentum and they've started spinning while keeping their hands outwards. And after some time, they basically collapse their hands over their heads, right? And they start spinning at extremely high speeds, right? And the reason for that, as soon as their hands collapse above, they have reduced their radius, not by a trivial factor, a significantly large number. And then it increases the inertia is a quadratic function of the radius. So if this is cut down, if the radius is half, then the inertia would be 1/4 of the previous value. But we know that the angular momentum is conserved, right? There is no additional torque coming from external world. So within this closed system, the angular moment is conserved. So previously it was J1 omega 1. This must always be equal to J2 omega 2. Let's say when their hands were stretched out, the inertia was some value. When their hands are collapsed, let's say the inertia is 1/8 that of what it was before, right? So J1 omega 1 equal to J1 divided by 8 times omega 2, which implies the speed at which this figure skater would rotate when their hands are collapsed over their head would be 8 times what it was when their hands were stretched outwards. Alright, so that's how they do this particular trick. Something interesting happens. Let's look at what's happening to the energy in the both cases. So in the first case, energy was half J1 omega 1 square. In the second case, do you think the value should be the same? However, we substitute the values, we can clearly see that it's not one and the same. So in the second case, inertia became J1 by 8 and the speed became 8 times omega 1 the whole square. Right, so that's 1 by 2 J1 omega 1 square times 8 square divided by 8 is just 8. So that's 8 times the energy that was in the earlier state. Right, so where does this energy come from? I said it's a closed system. Right, are we violating conservation of energy? Where I did say angular momentum is conserved in this closed system and I enforce that rule that angular momentum is one is the same. That's how we ended up with the speed. But that somehow seems to violate the energy conservation. Am I violating any law? Not at all, because the energy of this closed system is not just the energy stored in the rotational system alone. Right? There is energy stored within the human body in terms of all the ATP molecules that we saw before and the mass itself we have. So all of those are again energy that's within the system. So this is just one aspect of the energy that we are looking at where we are just looking at the rotational energy, but there are other stored energy in our body. Right? So whenever the figure skater goes from the hands outstretched to the hands close point, they are actually moving energy from their own body, right, by burning it in their muscles and transferring it into the rotational speed so that you can rotate faster. So when they go from the hands stretched out to hands collapsed, the energy is not one and the same. Actually, they have to do a whole bunch of effort and work to get to that state. So as simple as they make it look, it takes a lot of practice and effort to get to that point where they can transfer that energy almost seamlessly without us even realizing they're actually putting a whole bunch of effort to go from an energy state E1 to an energy state E2, which is 8 times what it was prior to that. Right, so with that, let's end today's class and we will continue on Friday. We'll look at one more example for the final element of this equation, load torque, tau L. And once we are done with it, we'll put all of these three together and look at a couple of examples of real world applications where all these three come into picture. Right? And once we are done with it, we might, if we have a little bit of time tomorrow on Friday, we will start to look at the fundamentals of power converters. Right? With that, let's end today. Thank you.